All right, for this second part, we're talking about quadratic regression, and this is no different, okay? This is no different than what we just did with linear regression, okay? It's the exact same, except instead of choosing linear regression, you choose a quadratic regression. So, what are we going to do with these points? Plug them into L1 and L2, yep. So we're going to go back to stat, clear out what you got. We put the x's in the, oh, I typed in a minus sign. 0, -1, and 1. And then we have 0, -2, and 6. Okay, so when you go to stat and you go over to calc, do you see the option that says quad reg? Yeah, we're going to choose quad reg. Okay, you're not graphing a scatter plot here, right? So you do not have to do the store reg EQ. Okay, just like before. The only time you need to do the store reg EQ is when you are graphing. So you can go ahead and hit calculate all the way through. And so our equation here is y equals 2x squared plus 4x. And then do I need to put the plus 0? No. Okay. So again, remember we talked about in the beginning, for linear regression, you look at L or R, just R, right? Everything else, you look at R squared. So what do we know about the R squared here? It's 1. So what does that mean? It's a perfect fit. Every single point is graphed by that equation. Okay? Y'all with me? Just got choked up on something. All right. So now that we know how to do quad reg, again, is it any different? No. Let's look at problem number 2. A player throws a basketball towards the hoop. The basketball follows a parabolic path. Oh my gosh, parabolic path. What does that tell you automatically? You're doing quad reg, right? Automatically, you know that you are doing quadratic regression because it says parabolic. Now, it says here, if the center of the hoop is at 1210, will the ball pass through the hoop? Okay? When you do your regression, do you include the center of the hoop in your L1 and L2? Yes or no? Why not? How? There is a point for it. It's only 1210. Do I include it or not? But if you include it, exactly. If you include that point, it would change your entire equation, right? So you do not include it. So in L1, we're typing 2, 4, and 10. In L2, we're typing 10, 12, and 12. So stat edit. Also, you can type over what's there. That's really fun too. What did I say those were? 2, 4, and 10. 2, 4, and 10. And then that would be 10, 12, and 12. Oop. So go to stat, go to calc, go to quad reg. We don't need to store our equation. Will someone read that to me? Negative 0.125x squared. X squared now because you're dealing with a quad reg, right? What's next? 75. Thank you. Plus 7. Okay. So now, from here, you can determine whether the hoop, like if the ball is going to go through the hoop or it's not, by doing what? Here. Yes. Plug in 12 into your equation. And then you'll get out a number, yeah? What's that number going to tell you? The y coordinate. And that's going to tell you whether he made the shot or didn't. What did we get out? 10. So did he make the shot? He sure did. It doesn't look like it, though. The picture doesn't. All right. We good? You sure? Okay, for the sake of time, I have to get through some more examples. But this physics problem, let's just talk about it, okay? Find a quadratic model. What are you going to do? Quad reg, right? Give me the equation. Okay, part B says use the model, so use the equation that you got to estimate the height of the ball at 2.5 seconds. What do you do with 2.5? Plug it in. Okay, what is the ball's maximum height? Okay, it's the vertex. Are you going to say that the vertex is at 163? No, absolutely not, okay? What do you do in order to find the vertex? Graph it, or what could you do algebraically? Get the equation and do what? Negative b over 2a, and then plug it in. Wouldn't it just be easier to graph it and do second trace maximum? Okay, so again, biggest takeaway from this slide. Do not tell me that the maximum is at 163. You don't know that for sure, correct? You have to graph the equation like we've done before. We good? Sweet. Okay, let's do problem number 4. And we're going to divide and conquer here. Okay? Problem number 4 talks about the price of milk. Okay? Now, I want you to give me the linear and I want you to give me the quadratic. Okay? So, half of y'all, right here. Hey, Davis, over. Y'all, give me the linear. Okay? The rest of y'all, give me the quadratic. What are we going to say 1955 is? 0. Right? So then what does that make 1980? 25? What does that make 2005? 50.
Oh, wait.
Anybody got the linear?
0.128x plus 17.
Can I get a confirmation? Yeah. What's the R value? 0.89. 0.89? Yeah, I'm fine with that. Can somebody give me the quadratic?
Y equals negative 0.00432 x squared plus 0.344x plus 16.5.
What's the R squared value there?
1.
Fantastic. Okay. So, with this slide, with this equation, I want to show you all the linear model was pretty good, right? But what do you know about that quadratic? It's perfect. Okay? So, which model is better a fit for this data? It'd be the quadratic one. And why is that? Because your correlation coefficient is 1. We remember we want it to be as close to positive or negative 1 as possible, right? Okay. Are we okay? You sure? Will's good. What about everybody else? Okay. All right. Flip over to the back. I think we're going to make it. So, we just talked about, we looked at the R and the R squared, right, to determine which one is the best polynomial. But there is somewhat choose the best polynomial. Okay? That is called the n plus 1 point principle. For any set of n plus 1 points in the coordinate plane that pass the vertical line test, there is a unique polynomial of degree at most n that fits the points perfectly. That is a little confusing, yes? Maybe. So let's break it down. So the part that on your notes it says this means that, what? Okay. Let's say you have 2 points. Okay, you're only given 2 points. That means the only regression that you can run would be a linear regression. Because how many points does it take to make a line? 2. How many points does it take to make a parabola? 3. If I need 3 points to make a parabola, is 2 going to cut it? No. So could you run a quadratic regression here? No. But what if you did have 3 points? What could you run? You could run a linear, and you could run a quadratic. Could you run a cubic? No. Okay. Do y'all see where the n and the n plus 1 are coming from? The n refers to the power. So if you want to run a cubic regression, right, power of 3, how many points do you have to have minimum? 4. Okay. If you want to run a quartic regression, what's the minimum number of points you have to have? 5. Okay. Y'all with me on that? Okay, that's the n plus 1 point principle. Now, for the sake of time, let's just talk about it. Okay? How many points do you have here?
4.
You got 4 points. So what are your options? Linear, quadratic, or cubic. Can I run a quartic? No. Okay. Now, when I run these regressions, what am I looking for?
Correlation.
The correlation coefficient. With linear, you want to look for r. Everything else, you look at r squared. And remember, we want it to be as close to what? Negative 1 or positive 1. Okay? Do y'all understand?
Yes.
We good?
Yes.
Sweet. All right. Let's do this application. This one's real important, and we'll finish here. On problem number 2, it says the table below shows annual consumption of cheese. That's gross. Per person in the United States from 1910 to 2001. It says find the regression that works. Okay? Now, how many points do we have here? We got 6. So, do we want to start with the linear? Probably not, right? Like, let's start with the highest, because as we saw in that milk problem, wasn't the quadratic better?
Yeah.
So always start with your highest regression to run. Because once you get that correlation coefficient of 1, buddy, you're done. Are we doing the 0 and all the things? So 0, 30, 60, 65, 85, 91. Oh, that's hard to do mental math. So when you run that regression, when you type that in, let's run the quartic. Let's run the quartic. Did the quartic give us a correlation coefficient of 1?
0.99.
0.9998. Okay. Did anybody run a cubic just to make sure? I would run a cubic just to be 100% sure.
4.997.
Ooh, okay, so quartic is the way to go then, yeah? By a thousandth of a decimal point. Okay. What's the equation?
For cubic,
Yeah, no, for the quartic.
-2.184.
X to the fourth?
Then 4.970.
X to the third, okay?
And then -0.29.
X squared?
Oh, sorry, 0.029.
It's okay. 0.029 x squared,
Yeah, then there's 0.545.
545x,
Then 3.998.
998, sure. Okay. Do we agree with this equation?
yeah.
Yeah? Okay. So now we want to use the model to predict 1980, 2000, and 2012, right? Well, what would I plug in if I wanted to do 1980? What would I plug in? 70, right? What would I do to plug in for 2000? 90, and then what would I do to find 2012? 102? Okay. We know how to do that, yes? I don't need to spend time doing that. What I need to spend time on is talking to you about this last thing. It says, in which estimate would you have the most confidence and the least confidence? Okay. Let's think about this. Between 1980, 2000, and 2012. Look at your table, right? Your years go from 1910 to 1940. So, which point, 1980, 2000, or 2012, which one would you be the most confident with fitting in that table? 1980? Why? It's kind of like near the middle of the table, right? Okay, so it's probably going to fall in line with the points that are centered around it. Which one would you be least confident with? 2012. Why? It's not even in the table, right? It's totally outside the table. Now, that introduces what we call extrapolation and interpolation. Okay? It literally means what it says. Okay? Extrapolation. That's extra. That's a number outside of your table. Interpolation. What does that refer to? A number inside the table. Okay? So when is it most accurate? Interpolation, yeah. All right, we are done with part 2. If you have any questions, let me know.